Okay, let's finish off our very coarse discussion of light. We talked about light as a wave. Oops. Let's now talk about light as a particle. Let me just remind you that with enough experimentation, the evidence mounted that depending on the type of experimental circumstance, light could behave like a particle, like a packet of energy that was localized. And of course, the Einstein went on to get the Nobel Prize for that very demonstration or the explanation of the photoelectric effect. And we'll have more to say about the photoelectric effect, but you probably remember it from your general chemistry or your high school days. Um, so, what are the important characteristics of light as a particle or light as a quantum of energy, a packet of energy? We know that for a photon, for a light quantum, the energy of the photon energy, photon energy, let's say E photon, and again, this is where the confusion comes in, where I use the letter E for the electric field, but now I'm using the letter E for the energy. Suffice to say that the energy is not a vector, right? So it does not have a direction, it just has an amplitude. Or, I'm sorry, has a magnitude. And so this is the energy of the photon, and we know that the energy of the photon is given by Planck's constant times the frequency of the photon of the what we refer to as the electromagnetic wave. And so, nevertheless, even though light is a particle, it has a frequency associated with it, just like any normal wave. But this is what the energy of a photon looks like. And what it shows is that the energy of the photon is larger, the larger the frequency. And so the faster the faster the peaks of what we thought of before as a wave are passing you, the higher the energy of the photon. Of course, that idea of peaks passing you was very much wave-like, and so we have to kind of try to reconcile the two ideas. But nevertheless, the photon has a frequency, the frequency of the electromagnetic field oscillation that composes the photon in some way, or defines the photon in some way. And so that's the energy of the photon. Now we know that the frequency is related to the speed of light and the wavelength, and so the photon energy may also be written as hc over lambda. So Planck's constant times the speed of light divided by the wavelength. Interestingly, the photon also has momentum. And perhaps it's not surprising, it's a particle. We think of particles having some kind of momentum. The weird part is that the photon is massless, right? It has no mass. And so the photon momentum, let's give it the small letter p. Again, it's a vector, right? The momentum has a magnitude and a direction. This thing is equal to Planck's constant times the wave vector. Now remember what the wave vector was. It's this vector that points along the direction of travel of the electromagnetic disturbance, but whose amplitude is 2 pi over lambda, 2 pi over the wavelength. And so this is h, where 2 pi h, oops, let me just erase this. 2 pi h over the wavelength times the unit vector along the direction of propagation. So let's call it x hat is the unit vector if the photon is propagating or moving forward along direction x. So let's just name this unit vector along direction of propagation. Direction of propagation, parentheses, along x in this case. So the photon has a momentum. Interestingly, this gives rise to the concept of radiation pressure, which is kind of a funny thing, but it can be measured. Now, radiation induces a pressure akin to a physical, kind of a physical force. Now, interesting thing. So, we define the energy of the photon, and that's what we're most familiar with. We talked about the fact that the photon also carries momentum. The longer the wavelength, the smaller the momentum. And so a photon of UV light carries more momentum than a photon of radio frequency. And remember that when we discuss light and electromagnetic waves, we, from a physics perspective, do not distinguish between the wavelength. We don't think of light of short wavelengths as light and electromagnetic fields of long wavelengths as not light. We think of all electromagnetic waves as light, and that those wavelengths can be long, they can be large. They can be long and they can be short. Short wavelengths corresponds to things like X-rays. A little bit longer wavelength would be UV. A little bit longer wavelength would be visible light, then near IR, then mid IR, then far IR, then microwave radiation, then radio waves, and so on. But all of that comes down under the same category of electromagnetic waves or light, spoken generally, not visible light as we tend to use that word kind of colloquially. So that's the photon momentum. The thing I want to, for us to at least comment on is the fact that when we try to think of light as having these dimensions of both wave-like and particle-like, if we remember back to what we said about the electromagnetic waves, when we drew these plane waves, these wave fronts, what we really mean is that these wave fronts extend for all time, for all space, and also they just keep coming, right? They never end. Or at least they just, continue to keep going. Maybe if the wave has been traveling for a very long distance, there are many wavelengths between the source of the wave, for example, an antenna, and the front of the wave front. That doesn't really jive well with the idea of a photon as a particle. Why is that? Particles, intrinsically, we think of as relatively localized things. They're not everywhere in space at the same time. They're somewhere in space. We're not going to worry about fine details like the Heisenberg uncertainty principle, which we will shortly. But for now, let's just imagine that we have a particle that is roughly in some region of space, and if it's flying through space, it is roughly here, and then later it's roughly there. It's not everywhere, but the electromagnetic wave extends through this enormous region of space. But nevertheless, if our photon has a frequency, therefore it has a wavelength, how should we modify our concept of a wave as applied to a particle, the photon, that is supposed to have some kind of wave-like properties? And so I don't want to get too detailed about this, but roughly speaking, this is how we might modify our ideas. Say, okay, so the photon is a particle. It is roughly localized in space. It can be everywhere. And so, perhaps, if we drew this in one dimension, the photon might look like this. Let us again make this plot of electric field amplitude. And now let me just make it very clear that I'm plotting the electric field, not the energy of the photon. Electric field. Again, the photon is moving along the x direction. And perhaps instead of having an infinite repetition of waves or wave peaks or wave crests that are moving through space, the photon, as a thing that should be relatively localized in space but still reflecting wave-like properties, may look like this. So that it certainly seems to have some kind of a wavelength. It is certainly moving at the speed of light, and so we'll have some kind of a frequency determined by the wavelength and the frequency having to be equal to the speed of light. But it also looks like it roughly extends over this region of space, delta x, so that it's roughly localized. It's not localized to a point, but it's localized to a region of space that is no longer infinitely long. No longer the crests and the peaks occurring, all the way back to the source, which may be very far away from some measurement point. This concept of this localized wavefront, effectively, is called a wave packet. And so photons should be thought of as wave packets. In a sense, you can see there's almost like an envelope function within which the wave is contained. In fact, what this looks very similar to mathematically is the electric field amplitude, in this case, being proportional to some kind of a product between sine of x times what's called a Gaussian function, a bell curve. And a Gaussian functional, in this case, we might write as e, the exponent e, right, the transcendental number e, times, or to the power minus x minus a squared, where a would correspond to the position x equals a. It corresponds to the peak. It's the center of this function. And so this wave-like property comes from the sine of x. The envelope that forces the sine of x to go to 0 far away from the center is given by the Gaussian function. So this and so on, this, a bell curve centered about A in this case. And so this envelope function mathematically ensures that the photon is relatively localized in space. So this is what we should think of. And in fact, this distance over which the electric field amplitude goes to 0 on both sides, this distance, should be thought of as the effective size of the wave packet, or can be thought of as the effective size, so that as it traverses through space, it will take about this bit of a distance to pass through whatever entity is feeling it. And so outside of these extremes, if you put a test particle here like an electron, it wouldn't feel any electric field. Outside of this extreme, a test particle here would not feel any electric field. Whereas if you had a true wave, not a wave packet, wave packet, for obvious reasons. Looks like a packet of wave, right? Wave packet. Here, the electron, far away from, let's say, the front of this wave train, would still be feeling some electric field, and so on. Whereas here, outside of this apparent size of the photon, the electric field goes to 0. What might this look like in kind of this three-dimensional world where we drew before? Well, perhaps it looks something like this. As the photon is flying through space, it might look something like this. If we use this, again, if we use this picture of signifying the peaks of the waves, where this is the wavelength approximately, or it looks like, and so the electric field would be pointing in this direction. And the same for all the other wave fronts, or wave trains rather, not wave fronts, and so on. And so you can kind of see, you can almost draw kind of a circle, or perhaps a sphere around it if it's truly in 3 dimensions, that would roughly say that approximately the size of the photon is this, using the idea of size very loosely. Right, and using the idea of a wave packet at this point relatively loosely too. But that's all we need to say to get a physical feeling for how to possibly reconcile the idea that the photon is a particle and therefore is somewhere. Maybe that somewhere is not fully defined. Maybe it's a region of space of some kind, but it's a finite region of space within reason, as opposed to a wave that extends ad infinitum, or at least possibly all the way far away back to the source of the electromagnetic wave or field disturbance. And that, I think, is enough to say about the photon. Let us now use this idea of the particle of light to define another property of light, now that we can consider it to be composed of photons, or particles of light, and that is of light power. What is light power? Let's define light power. Light power, or the power of light, is the amount of energy, let's say photon energy. Let's not say photon energy. Let's just say electromagnetic energy. electromagnetic energy that is incident or falls on incident on a surface per unit time. So let's say in 1 second or 1 minute, depending on which units of time you want to use. So the idea is that given that the electromagnetic wave, I shouldn't say electromagnetic wave. The idea that light is made up of particles that carry energy with them and that can strike a surface, the total amount of energy that crosses that surface or strikes that surface in some amount of time is the power of that light. So for example, if your light beam has many photons in it, the power is going to be great. If the photon beam has few photons in it, the power is going to be small. And so the physical circumstance that we imagine is there's some kind of a surface. The surface is being bombarded by photons that I'm indicating by these arrows, and so on. And we effectively measure the total amount of energy that is deposited or goes through the surface in a given unit of time. And that's the power of light. And given that the energy of the light beam is made up of the packets of energy of the photons, the light power is almost synonymous with the number of photons in your light beam. Of course, what also matters is the energy of an individual photon, right? So a beam that contains 5 photons, or that strike the surface in, let's say, 1 second, let's say 5 photons strike the surface. If the photons are X-rays, that's a lot of energy, even though there's only 5 photons. But if the photons are radio waves, or radio of a radio frequency, or maybe they're infrared frequency, then that's a lot less energy, even though the same number of photons strike the surface. Right, so this is power. So power, let's again put this, so light power, let's give it the letter capital P for now, is the sum of the energies of all photons that strike a given surface in time delta t divided by that time delta t. So it's per unit time. The longer you wait, the more photons will strike. But if you take the number of photons or the total energy that was deposited or passed through a surface in that time delta t and divide by that time delta t, so the amount of energy per unit time, that's the power. And derived from this concept, light power, is the concept of light intensity. And so light intensity goes just one step forward and says, okay, this is the sum of the energies for all the photons that strike a given surface in time delta t, where that surface can have whatever area. The bigger the area, the more power absorbed by the surface or incident on that surface. But suppose we wanted to isolate a small, let's say, unit area here and say, okay, maybe instead of worrying about the fact that the total power delivered to the surface depends on the actual area of the surface, what if we just want to characterize kind of the strength of the strength of the light beam, without worrying about how wide the beam is. Suppose the light beam can be very wide and therefore hitting a big surface, or the light beam can be very narrow and hitting a small surface. But per unit surface, in one small region of space, how much energy is being deposited, how much energy is crossing that surface. And so we may take the surface and we may take the power and divide it by the area of that surface. And the power of light divided by the area that it strikes or I'm sorry, by a small area, is the intensity of the light beam. And so the intensity of light, or the light intensity, is, call it I, is the total energy that falls onto an area A. Let's say this is A. In time delta t divided by both delta t and the area. So the total energy that falls on a surface per unit time per unit area. And so if you increase the area, you will also increase the total energy. That is, or rather, if you increase the width of the beam, of the light beam, whether it's laser light or light bulb, whatever it might be, a flashlight, if you increase the area of the beam, the total power in the beam will also grow, but the intensity will stay the same in principle. And so this quantity asks for how much does a small area, how many photons or how much energy does a small area receive in a small time interval delta t. And so you would look at the surface that you're striking, wait for let's say a second, total up the total energy that crossed that area in that 1 unit of time, that second, divide that total energy delivered by that area and by the unit of time, and that gives you the intensity. The total energy that crosses the surface in a unit area in a unit of time. This idea of light intensity is a type of what's called flux. And so flux is when a flux is some kind of a quantity that is traversing in space, that is traveling, and that is crossing some kind of a surface. And so, maybe you can think of a water flux, an electron flux, whatever it might be. Okay, and I think that is sufficient for our purposes.